I'm Carrie.
I'm Sissy.
I'm Chung.
And today we're here to talk to you about an intelligent eye for the visually impaired. So before we start, we'd just like to thank Jackie, our academic mentor, and Jimmy, our Lenovo mentor. They've been great. They've supported us throughout this whole ordeal, and we would have nothing if it weren't for them. So thank you. So fact. Many of you may not know that an estimated 285 million people in this world are visually impaired. That means that 285 million people in this world are in need of an intelligent eye, a technology that can help them navigate their surroundings, find their everyday objects, and improve their quality of life. So for this project, Lenovo tasked us to build the first steps of an intelligent eye. And when we were given this assignment, the picture that we had in our minds was, we wanted a program that could scan an image for shoes, and it would be able to draw a red box around any shoes that it found. So our overall product was an iPhone application. A user would take their Android phone, use the camera to take a picture, and our application would send this picture to our server, which hosts our code. Our code would detect the picture for shoes and send that result back to the phone. And the phone would tell the user, I have found a shoe, or no, I'm sorry, try again. And in this way, we think that this is the first step of a technology that can help all visually impaired people find things that they need every day in their lives. So in this presentation, we will first talk about machine learning and convolutional neural networks to give you a background of the techniques that we used. And then we'll go on to our project, and we'll talk to you about our model, our data, and some results. And at the end, we'll give you a demo of our product, so be excited. Okay, so to start, machine learning is a branch of artificial intelligence. Arthur Samuel, one of the pioneers of machine learning, defined it as a field of study that gives computers the ability to learn without being explicitly programmed. It's a theory that focuses on prediction, based on known properties learned from the training data. So our machine is given a set of images, shoes images, and it knows beforehand, image A is a shoe, image B is not a shoe. And it takes all of this data in, and it tries to find commonalities between the shoes pictures and the non-shoes pictures. And so given any picture in the world, a picture that it has not seen before, it can say, that is not a shoe, or that is a shoe. And so that is the power of machine learning, to generalize from a smaller subset. So now we move on to convolutional neural networks.
Thank you, Carrie. I will follow on to talk more about the convolutional neural network. Convolutional neural network is a typical example of machine learning and deep learning. Inspired by the animal central neural system, machine learning scientists developed the structure of a convolutional neural network, which mimics the structure of an animal brain and is capable of machine learning and pattern recognition. Actually, convolutional neural network is largely used in our daily life in the computer vision part and also the speech recognition part. You're probably using like dozens times a day without even knowing about it. It can exist in the system of Apple Siri service using the speech recognition, and also the Google Street View using the machine vision, like give you the address of the place that in the picture you send it, and also maybe in the Google's spam email blocker. And given those solid proof of the powerfulness of convolutional neural network, we decided to try convolutional neural network for our project purpose. And now I'll follow by talk more about the structure of convolutional neural network. Like the graph here says, this is the general structure of a CNN. First is the input part. Like for shoe detection purpose, the input is like a matrix that incorporate the information in a picture, like a shoe picture or a non-shoe picture. Then those matrices will first go through the feature extraction model, where we'll generate a feature vector. Those features can be like the curves of a shoe or any vertices in it, and the feature vector will tell about the existence of some certain feature. And then those feature vector will go through those trainable classifier model, and where it will go through a huge amount of calculation to generate a class score. where the system will make prediction about the image based on those class score. For example, in the shoe detection purpose, like if the score is closer to +1, the system will tell it is a shoe, and if it is closer to -1, it will tell it is a non-shoe. And that is the general structure of convolutional neural network. If we want to go deeper into the structure, we'll talk more about the two models separately. First is the feature extraction model. Like the graph here says, first is the input part, like the matrices that incorporate the information of the pictures. And it will first go through some convolutional calculation to generate those feature maps. Like here in the picture, there are 4 feature maps. And they can be the curves of the shoe or the logo on it. Then those feature maps will go through some subsampling calculation. Those subsampling calculation will averages those entries of the matrices to generate a greater pattern based on those features. So that in the following convolutional calculation, it will extract a greater feature based on those patterns instead of the small features. And this is the structure of the feature extraction model, so the alternation of convolutional layers and subsampling layers. Then it will go through the trainable classification model, where the structure is more like the general neural network. Here, the input will be the feature vector we've got from the last model, and it will output a number. After interconnected calculations, the output, like I said before, if output is closer to +1, the system will tell it is a shoe, and if it is a -1, the system will tell it's a non-shoe. And that is the structure for convolutional neural network. And here, a question will come naturally, how does those algorithms come from? How can we figure out which algorithm to use? The answer is the machine can learn itself. The learning happens through the training process, but first we need to show them a huge amount of data so that the system can learn which is a shoe and which is not a shoe. And the data looks like this. It's basically a coordination that consists of 2 parts. For the first part is the training sample, if it is a shoe image or it is a non-shoe image. And for the second part, it is a label. If the first part is a shoe image, the label should be a +1, and if in the first part is a non-shoe image, the label should be a -1. And for the system, the entries of the matrices and the neurons in the neural network are interconnected by weighted, trainable parameters that the machine can learn itself. After seeing those data, the machine will learn by adjusting those parameters in the criteria of minimizing the error rate. And that is how the machine learns itself. And here, that is so much for the convolutional neural network, and I'll follow on talk about another important technique that we use, which is the multiprocessing technique. Here we make use of the GPU, which is short for Graphics Processing Unit. GPU is a complement for CPU, and it is an element that you can insert in your computer to help it to calculate faster. For a general CPU, it only contains multiple cores that can calculate simultaneously. But for a GPU, it contains tens of thousands of smaller and more powerful cores that can make calculations at the same time. For our project purpose, the similar calculations are conducted on several data. If we can make use of the GPU, those calculations can be done in a click, so that the training time for our project will be largely reduced, say by 60% or more. If you consider our project, we have hundreds of thousands of data, and we need to make new trainings for each attempt we've ever made. So in total, we calculate through those hundreds of thousands of data 20 times. So the use of GPU has largely reduced the time we've need, and that is for the multiprocessing technique. And that is so much for the background of our project. And I'll pass time to John to talk about our project.
Thank you. Let me talk about the overall design of our project. We use convolutional neural network. And as he said before, there are 2 parts in our model. The first part, convolution. We use 3 convolutional layers, alternating with 2 subsampling layers. And in the network part, we use only 1 hidden layer because we think if there are many nodes in one hidden layer, it will be enough to represent all the information we want in our images. And next, the suggestion. It says, as it said before, we want our features, but what features do we want? We focus only on the important features like the shapes and the curves from our shoes, but we ignore the features like the color, the texture, the lighting, and the size. So we will turn our images into grayscale. And since we want to tell our models to learn the differences between the shoes and non-shoes, we need to show our models the pictures of the shoes and non-shoes. And we'll choose the indoor objects as our non-shoes data. And here is a concrete example of our non-shoes objects. And okay, first of all, we need to get our data from the samples.com, which is like Amazon, but especially for the shoes. And after we got all this data, we need to rotate it to get the pictures from different angles and return into 200,000 images. And here are some examples of how we rotate these objects. And the accuracy. Our model can achieve 99.99% accuracy on our testing set, but it didn't work very well in the real world.
If that is the real world.
Yeah, if that is the real world. As you can see, there are 5 shoes in our imaging, but our model can detect only 1 shoe correctly. And you can see there are some still false alarms here. And so we figure out the reasons. The problems, it is the problem of our backgrounds of the shoes data, because the backgrounds of our shoes data is all white color, and it becomes the dominant features of our images. When our models are detecting, it detects the objects by its backgrounds, but not the shoes itself. So we try another method. And at this time, we focus the side view only because we want to minimize the area of the background. And second, we will replace the backgrounds with the noisy one, the indoor images, to make the pictures look more realistic and more noisy. And now we achieved 98% on our testing set, and you can see it works pretty well on the real world data, real image. And there are 5 shoes here, same as the previous one, and you can detect all the shoes. And here are some ideas for improvement. And we want our model can detect multiple views instead of only the side views. And we want our model can detect multiple styles like the high heels. And we want our models to become more powerful to detect other objects. And we may try to provide a faster implementation for training and testing. And then we'll show you our demo video.
Well, we'll first do a webcam demo, so you get to see this in real time. So can we invite our mentor, Jimmy, up to do the demonstration? He loves this, so.
Yeah, I think you can just put the
Yeah. All right, it's working.
Yeah, so I'm gonna just use my own shoes to do this live demo to you. All right, so I'm gonna take off my own shoes. Yeah, so maybe just 2.
Can everyone see this? If you can't see, feel free to come up and gather around.
Right? Do you see it? Yeah. Right, so I can just, I can also flip the shoes and
You can show that to us.
yeah. So the system is also gonna detect the shoes in real time. All right?
And that is the real-time show, and we also have a video for the actual use of our application.
Oh, where's my shoes? I think I asked to help me.
I am looking. Try somewhere else.
Well, I need to try somewhere else.
I am looking.
how our application can be of real use.
Okay, so acknowledgments. We'd like to thank Jackie and Jimmy again, and we'd like to also thank IPAM, RIPS, HKUST, all the other acronyms, and questions.
Yeah, that's a question.
How did you get these accuracy values?
Okay, so we have several 100,000 images, and they're all images that look like these. So this is going to be a shoe image, and an indoor image would basically look like that on the right. So we've separated out about 80% for our training set. So these are going to be images that the machine sees and is learning from. And then the rest of the 20% would be our testing set. So these accuracy values, the 98% accuracy and the 99.99%, those were based on the testing set. So images that are similar in nature to the training set, but the computer hasn't explicitly seen.
Oh, okay. But are your training set images like these, or are they?
No, they're
without
like
background?
these.
So they are without background.
Right. They're exactly they could just as well have been in the training set, except that we filtered them out specifically and allocated them towards the testing set. Yes.
Do you use different styles of shoe, or are they all, it looks like basketball or rubber shoes?
This time we only use the sneakers.
Like
We will
the
try
athletic
making
shoes.
sneakers.
Athletic shoes from Zappos.com. Yes.
How to determine if a program really detects a shoe in a real image? I mean, in that picture, yeah, I saw a lot of bounding boxes that does not really 100% overlap with the shoe image in that picture. So how to determine that?
So these bounding boxes were drawn using a multi-view, a multi-scale algorithm. Because given a picture of the shoe, it doesn't know how big the shoe is inside the picture. Because we trained them on these images, and these images are uniformly 32 by 64. So for these types of detection, we needed to use a multi-scale. So we would scale the picture to like 320 by 240, and then we would scale it again to like 120 by 80, or something like that. And it would detect at each level. And so these smaller bounding boxes that you see comes from that. So it's not perfect, but it's good. It's seeing a lot of shoes, and they're right.
Yes, that's one more.
Oh, wouldn't people remember where they put their shoes? Why would they need such a map?
Now this is an application just for shoes, but using similar methods, we can apply this application to other objects like glasses for all the store side people they may use. And also because for shoes, we have plenty of samples we can easily get. So that is the motivation for us to use shoes for this demo.
Okay, so I have one question. So right now, the cell phone is just to use to take a picture, and then the picture will be sent back to somewhere.
Yeah.
Would it be possible to do everything offline, so I can do all the computation on the cell phone without sending back to a more powerful computer?
The Android phone is not powerful enough to do all this computation.
Okay.
But in future, the cell phone evolves to a higher level, we can do that.
Okay. Yeah, because it's getting more like a computer already. So.
Because even the testing part, we need to use the GPU to test the
For speed.
Yeah, for speed.
So if this can get smushed to computer science.
Okay. So we still have to wait.
Yes.
Okay. So any other questions, comment? Okay, then let's thank the Lenovo group again.